So let me quickly open yesterday's so that we start yesterday's work. Yes, the output. Okay, the Dr. Ikubo talked about the output of yesterday. So if that's the case, maybe I will just
interpretation
of the output of the. Is it the one we run?
No, don't start on. It's only the interpretation I need.
Okay, that should I will just run the.
The one we run with that incident.
Yes, I will.
Only the output is what I need. Interpretation.
No problem. Yes, that's obesity. Okay, let me just run it now. Analyze cross-tab, obesity, CVD, obese. Age group. Oh, wait, I didn't even know that I was not showing it. I was not showing it, right? Can you see?
No, yeah.
Yeah, let me just show the result.
Output.
What I was showing you. This is the result output of what we did yesterday. Let me start from the beginning. So you know that you split it. Normally, if we didn't split it, it will just be the total that I bring out. Obesity, yes or no, CVD, yes or no. Since we are split it into two strata, strata are people that are less than 50 years, people that are 50 years and above. So it's do the 2 by 2 table also for less than 50 years, for 50 years and above. So the two strata did the analysis for. So if you scroll down, don't want noise. If you scroll down, if you look at the crude odd ratio for odd ratio, okay, this is risk relative, okay. If you remember this crude odd ratio, look at this crude odd ratio, you see 1.93. So when we when you do everything together, this crude odd ratio is 1.93. Let me look at it, 1.93. But when you now do it separately, the odd ratio for the crude odd ratio means the odd ratio for all of them together. When you now stratify, the odd ratio for less than 50 years is 1.48. Can you see 1.476, 1.48? And the odd ratio for the other group, greater than 50 years and greater, is 1.54. Can you see? And you see the funny thing. Both 1.48 and 1.54, they are less than 1.93. The crude oil ratio was 1.93. So when you split it, each of them they are lower. So if you look at the odd ratio also for the 1.93, the confidence interval does not cross 1. It shows that it's significant. It is telling you that the people that are obese are 1.9 times more likely to have coronary heart disease, cardiovascular disease. So now, and it's significant. But if you look at this odd ratio for the each group that are even less than 1.9, they are not significant. Look at it. One is from 0.7 to 3. This one is from 0.88 to 2.7. Can you see? So they are not significant. That shows that it's telling you something that, okay, this thing is either a effect modifier or is a confounder that age. So you now want to analyze further to separate the father is a confounder from where it is a effect modifier. So if you do the homogeneity test, you want to test that is it homogeneous. That is, the meaning of homogeneity here is that the odd ratio in his strata, in his stratum rather, in the different strata, are they the same? You know, if you look at it, the value look close, 1.48, 1.54. It don't need to be the same exact figure before you can say they are the same. If something is similar, the value will be close. So sometimes you may not know how close it is unless you put it to test. The test of homogeneity to see that this thing I'm seeing, is it the same or are they different? So if you look at it, we discussed yesterday, effect modification, interaction, heterogeneity. Those are the different names for the same thing. When you say something is effect modifier, that shows that there's an interaction. If you say there is effect modification, it's the same thing as say there's interaction. It's the same thing as saying there's heterogeneity. What it means is that for different level of that variable, or for the different strata produced by that third variable that may be a effect modifier, the odd ratio will be different. That's what it means. So we can see that the values are different, but we want to see, is it actually different? Because they look close also. So if they are actually different, that shows that there is heterogeneity. That shows that there is effect modifier or there is interaction. If they are different. But if they are the same, that shows that you cannot say there is effect modifier. That shows that that particular thing is likely to be a confounder. So look
what you are looking at, you are not looking on whether they are significant, but whether the values are the same. Like this one, I'm seeing 0.932 and 0.932.
The 0 from what?
You are not looking whether they are significant or not, but whether the two values are the same. Like here, it's 0.
It's P now.
It's P now.
Here is 0.9.
That is what is telling you that they are the same. Because if the P is less than 0.05, you now say they are different. There's a significant difference. Here now there's no significant difference between the two.
The P is the same.
Yeah, it's the same.
Okay. So it's the P you are looking. Yeah, okay.
Yes. The P now is the one that will tell if there's a significant difference or not. So this one is showing us there's homogeneity.
What does Tarona stand for? Tarons.
What is it? It's another test. It's doing the same thing. Look at even the value are the same. Is any of the, just like when you have maybe different chi-square. You see, likelihood ratio chi-square, basic chi-square, doing the same thing. That's what this one is. Actually, both of them are chi-square. They follow chi. You know, we have already discussed that many things that follow chi-square. Many chi-square distribution will give you different name in different places. So if you look at its chi-square and Breslow, you know, the issue that Breslow will describe it with some formula. Tarun describes, so they are doing it and eventually end the same thing. Or if even the value are not similar, maybe just slightly different. But sometimes to be like this one is the same. I don't know if you understand me now. It's just like if you remember basic chi-square and likelihood ratio chi-square. What you see slightly, the likelihood ratio chi-square is usually slightly bigger, small. So it's different way of calculating chi-square, but the value is just slightly small. It's different. So it's the same thing with this Breslow Day and Tarun. Now, so we have established that there is no effect modification. So we now want to see that, okay, this confounding, how important, how significant. So the test for conditionality now, can you see? You try to see, look at it, almost what it's telling you is that even the effect of it's trying to compare the eventual odd ratio. If you look at the odd ratio, Mantel-Hansen odd ratio 1.52. Look at it, 1.52. We want to see how significant it is. Yes, I'm not significantly different from the crude, and that is what this one now did. So if you look at it now, both Kroken and Matte-Hansen chi-square also of C, if there is any, can you see, is almost significant. It just almost. But to me, if something like this one, I want to take it as it because 0.064. So that's just it. So now the interpretation now is that since you can see that effect modification is not there, and this one also is not significant. So the best way is just to report. You can just report the crude oil ratio. Yes, you record the crude oil ratio, and you can report. Yeah, you record the Matte-Hansen oil ratio and crude oil ratio. So for the fact that there's homogeneity across the other one, you don't need to say this is for each stratum, because what is telling us that for each stratum they are almost the same. They are the same. For each stratum they are almost the same. And we already said that when there is a confounder, you don't expect them to be different. The oil ratio for each stratum should be very close, and that is what we are having now.
So now the last one is for confounding. That is this MH common oil ratio estimate is to test for confounders, while the other one, the homogeneity, is to test for effect.
If there's effect multiplication, exactly.
Yeah.
If you look at this one now, is not. If you still look at the Matte-Hansen oil ratio 1.52, look at the confidence interval 0.97 to 2 point something. You know, we said it's almost, it's not significant. See, what is there? There is a confounder, but the confounder is not much significant. I don't know if you understand me now. But you may encounter some, you see that the significant effect is here. So don't worry, we are going to run the same data set now with logistic.
Sorry, can you go? Can you scroll up a little bit the estimate table? Sorry.
Okay. Okay. Yeah.
Yeah. Why is yes? There is bracket yes / no. What's the meaning of that?
Yes, what is telling you is that
there's yes before no.
Yes, what is telling you is that no is the reference. What is telling you is that the people is talking of the exposure now. These people that are obese, how many times are they more likely to have CVD? The people that are obese more than the people that are not obese.
The yes one.
The yes are the obese, the no are the not obese. So it's telling you that it's the obese. You are trying to say how many times. If let's say we coded the obese as 1 and the other way around now, the odd ratio would be 0 point something, be less than 1. I don't know if you understand me now. So if you look at the cohort also, he said that these two now is the relative risk. But he said that the relative risk, if it is you are looking for CVD, yes, CVD, no. If what you are looking for is that how many times people that are obese are more likely to have cardiovascular disease, that is the first one. How many times people that are obese are not likely to have cardiovascular disease, that is the second one. Can you see? If you say they are not, so that's just it. So that usually give two cohort, two risk estimate, which is the relative risk. All of them are risk estimate. But the first one is odd ratio. The other one
also the second one is RR.
Relative risk. Thank you, sir.
RR.
Yes, relative risk. I think we can proceed now.
Yeah, sure.
That's great. Yes. So let's talk about logistic regression. You know, I'm so passionate about this because I know that all of us here, we are health professionals, and this is the commonest statistical modeling in medical literature. And it's because the doctors want to make decisions about who to treat, who not to treat, use a particular method to treat. who has the disease, who doesn't have the disease, so that I will treat. So because his own is, you have the disease, you don't have, you need treatment, you don't need treatment. So either of the two decisions. And because of that, that's what makes regression to be popular in medical parlance. So there's no way you can push it away, reduce the volume of that thing. There's no way you can push it away. It's a multivariable method for modeling the relationship between multiple independent variable and a categorical dependent variable. So that is when we are talking of modeling here. When we say multiple independent, that is, we have many independent variables. That is when we are talking about multivariable analysis. So I don't want to emphasize whether it's multivariate or not multivariable. I've already established long ago that it's multivariable. So anybody that call it multivariate is just a form of misnomer. Now, logistic regression analysis studies the association between a categorical dependent variable and a set of independent or explanatory variables. It is a type of generalized linear model. You know, there's one time Prof asked a question about this general and generalized linear model. So, logistic regression is a generalized linear model. Linear regression, of course, is both general or general. When we say generalized, it's a more bigger umbrella. So, linear regression and NOVA, they are under general linear model. So they are also under general, it's the same general linear, you now extend the same thing to something like logistic regression, Poisson regression, and other form. They now call it generalized linear model. So the difference between general and generalized now is that the outcome you are projecting, you are predicting for general linear model, they are continuous, they follow normal distribution. They are continuous variable. So when you want to extend the same thing to outcome that you do not follow, they are not interval or ratio, they are not unbounded, you have to now create a link, function link, for them to be able to function. Listen, for them to be able to appropriate, you must transform them using a function link. So when you are able to transform, you now invite them into corpus. That is why now, okay, it's a generalized linear model. So when you extend the linear model, general linear model, to include those ones that are not normally distributed, the outcome that are not normally distributed, you now call the umbrella generalized linear model. So you're going to see that the generalized later, you're going to see that there are two stages for you to make them. For all those things that don't follow normal distribution, for you to be able to use linear model for them, there are two stages way to work. We're going to see. It is a type of generalization here for response variable where regular multiple regression does not work very well. Type, we have two categories of outcome when it is binary, or you can call it binomial. You guys just see now. Binomial, binary or binomial. Binomial. It's another name. Binary or binomial, two categories of outcome. Multinomial. Why I try to put that binomial there is that so that it can be in line with the other one. Multinomial. More than two categories of outcome. So when there are two, dead or alive, and that is the commonest. In fact, when people talk about logistic regression, that's what they refer to. You just see that the outcome is binary. Multinomial, more than two categories of outcome. Ordinal, other categories. So when the more than two categories of outcome are ordered, because the categories of outcome, category cannot be ordered if it is two. It has to be three or more for it to be in order, to be ordered. Before you can say something is increasing, close the door. Before you can say something is increasing, it has to, it's not just two stages. You cannot just have 1, 2 and say it's increasing. You must have 1, 2, 3, at least. So order, when the category are ordered. Then conditional, when you usually use for match data, especially match case control, where you have match case and control. So the type of you call it conditional because there is a condition underlying it. So the name logistic regression is often used for binary. So use binary or binomial. When you say logistic regression, people usually mean binary. The dependent variable has only two values, two outcomes, two possible values. The outcome has two possible values. One of the assumptions of the linear model is that the relationship between the predictors and outcome is linear, which we have done in linear regression. When the outcome variable is categorical, this assumption is violated. So, because in the linear something, in linear regression, we talk about correlation. We say two variables, they have linear association. And that's what extends to regression. But when you are talking of logistic, when the outcome is categorical outcome can never have linear relationship with other, even if those other ones are linear, are continuous. One way around this problem is to transform the data using the logarithm transformation, which is a way of expressing a non-linear relationship in linear way. Many a time, if something is non-linear, when something does not follow no matter is non-linear as you want, you can transform it using logarithmic scale. So the intelligent people play, you're going to see the way they play around it. It's something that is very interesting. Now, so the logistic regression uses this transformation to express the linear model equation in logarithm term called a logic. I'm going to explain it. You have a logit. So there are a number of alternatives. You can use complementary log, probit, but the one we are talking about is logit. So, and that's what maybe another time if we have anything related to probit or whatever, but it's not common. We talk about it, but this one is logit model, logistic regression. The logic function is particularly popular because its results are relatively easy to interpret. It's more popular than log and probit because the results are relatively easier to interpret. However, it requires logic link function. That was what I said the other time, that for you to extend general linear model to others, so we now put them under the umbrella of the generalized linear, you need a link function. So what we continue that, let's just quickly look at these pictures speak more than words. Let's look at linear regression versus logistic regression to see. If you look at the linear regression line, can you see? If you remember that first one, it's like what we did before in linear regression. The aim is to predict continuous value output. While output value can be either possible entire number, that is, any possible can be any number. When you are predicting like issue of, remember when we tried to predict peak expiratory flow rate or pulmonary dead space from height. All these things, the outcome, the pulmonary dead space, the can be any number. So that is one, it can be any number. There's nothing that stops it, there's no limit. Though naturally, you may not see number as high as that. There's nothing stopping it. There's no rule stopping the value from going up or going down. That is the meaning of that. But when you come to logistic regression, the aim is to predict the label for input data. Output is categorical, binary, true, false, 0, 1. So here, and when there are two options, you code one 1, you code one 0. There are also two options you can belong to. You see, they give you two options. You can only be in any of these two classes. It's different from linear regression that the value of that can be anything. It's free. It's free to vary any degree. But this one, you can only vary only two options. So can you see that? So that shows that look at this graph. The value cannot, look at this scatter graph for linear regression. Look at for this one. You see that the one, all those dot, they are around that one, that line, horizontal line one. For the 0, they are there. There's nothing in between. But it's unlike this one. So because it's either one, for each value of x, f can have many values, but each value of horizontally, it can either be 0 here, down here, or is up there, 1. So it does not, it has limited. That shows that if somebody have x that is instead of the corresponding y to go up, it cannot. Either you are, it's just like anybody that score above this, they just say, you know, the Americans say pass or fail. Pass or fail. Sometimes they just say that they like close marking you do. See, you don't believe that anybody can score too high. Too high. So there's a limitation with logistics into 2 classes. This one is still saying the same thing. So if the line you predict for linear regression is a straight line, can you see? This one will come with one sigmoid, you know, sigmoid line, like this. Something like this type of line they use for population prediction. So we'll talk about that later. So for us to actually know the way they do the transformation, they go about it, we need to understand, come back to the meaning of odds. You know, yesterday I was trying to prime up, look at probability, odds, odd ratio, logit, just to burn some time yesterday. So we discuss it again here. Odd of an event is the ratio of the probability that an event will occur to the probability that it will not occur. We have established yesterday. Odd is probability over 1 minus probability. If the probability of an event occurring is P, the probability of event not occurring is 1 minus P. So the corresponding odd now will be P over 1 minus P. I think it's very clear. Please, if there's any question, you can, don't hesitate to stop me. If I have your question, you can raise. Yeah, okay, go on.
So, sir, my question is just about, I know you were trying to explain that probit log.
Okay, forget about the probit and log. Forget about probit and log. Yes, log is logit. We want to explain that logit. Just forget about. We'll be talking about probit. It's just one way. You know, we said that for you to make something that is not does not follow normal distribution, something like that. Log, you have to do transformation. You can do probit, log, or logit. It's logit you want to explain now. So I'm just giving you option. You know, many options, but the option for logistic regression is logit. Okay. And the option for logistic regression is logit. And the logit you want to explain now, the origin, how the logit comes. Now, we first of all want to understand odds, what odds mean. I think everybody understand probability. So odds is probability over 1 minus probability. So we'll move on. Now, we talk, I don't think we waste time here because I've discussed this in many times. That risk, the probability, and the odds. What is the difference there? We have already said it yesterday that probability is from 0 to 1, odd is from 0 to infinity. And for you can try it yourself. Probability is 0 if you use the same formula, P all over 1 minus P, odd will be 0. If you increase your probability to 0.001, this is what the odd it will give you. If you increase your probability to 0.5, which is half of 1, your odd will be 1. You also know, we know that odd is P over 1 minus P. So if P is 0.5, so that's that odd will be 0.5 over 1 minus 0.5. So it will be 0.5 over 0.5, which is 1. So odd is 1 when probability is 0.5. When the probability rises to 1, which is the highest it can be, odd will go to infinity. And you can prove it also. If odd is P over 1 minus P, probability is 1, P is 1. It's going to be 1 all over 1 minus 1. Which 1 minus 1 will be 0. 1 over 0 is infinity. Anything over 0 is infinity. So can you see now? So it's very funny. The probability has a range from 0 to 1. Odd has a range from 0 to infinity. When probabilities travel halfway from 0 to 0.5, which is the half of its journey, odd has double its own that journey to 1. Can you see now? That journey of probabilities has doubled it. So when probability now finish its own journey, odd has gone into space, has escaped to infinity. So can you see? This is the graph is showing the same thing. You plot odd over probability. That you will not get a straight line. You will see, because odd is not on that. Look at the probability. You know, we say we have probability problem with probability because it's fixed. Because the logistic, the outcome you are trying to get, you are going to measure. You say it's fixed between 0 and 1. You don't like it. You want something that can give you leverage to extend. So if you calculate from that probability, calculate odd. The odd itself has given you its own problem. Its own problem is that, look at it. When probability is 0.5 now, we have said that odd is 1. When probability increases to 1, this one, it turns the graph to infinity. So there's another here. This one, to explain further the problem, you are trying to get a solution. You enter another problem. So look at it. This is the probability itself. Apart from the fact that we know that that's its own good aspect, a fact that is between 0 and 1. But if you take sample many times, you can follow normal distribution. But that one is not useful for what we are looking for, because the logistic regression is one situation. One, we are talking of one output, which can either be 1 or 0. So you see that we have already talked about the problem that will give us. You cannot stretch the outcome, it limit the outcome from between 0 and 1. So the problem where I'm showing this one is that the odd itself, can you see by the virtue of that graph you saw before, it cannot follow, can you see? It cannot, it doesn't, even if the odd itself does not follow normal distribution. Can you see the graph? Now, what now follow normal distribution and also extend, give us what we want? It follow normal distribution, then it gives us a lot of leeway, is transforming the odd further by calculating the logarithm of the odd, which is log odd. It is what's called logit. Logarithm of odd is logit. There are some other things that we can come back, but it's not necessary I explain it here. I can come back because I don't want you to confuse. But this is the message I want to pass here. Why using logit, log odd? Because we know that the probability can follow the probability can follow our distribution, but the problem we have, it has leading us between 0 and 1, or 0 to 100%. Cannot go beyond that. But the odd that can go beyond that is 0 to infinity, but it doesn't follow normal distribution, because if you look at it, it's skewed. It's skewed because from when probability travel halfway, he has traveled double probability, but you cannot say we travel his own halfway. When probability completes its second halfway, odd has gone to infinity, so it's skewed. So when you now calculate the logarithm of the odd, it gives you the logit. That one, what it gives you is that it gives you a value that ranges from infinity to infinity. Infinity on the negative side to the infinity on the positive side, and is now normally distributed. I don't know if you want to ask questions concerning that. I don't know, do you get it now? You get it why people now, the solution we are going to now, We are looking for outcome that does not limit the value. Just like the way probability, because the logarithm either 0 or 1 is probability from 0 to 1. The funniest thing is that it doesn't even take value between 0 and 1. It takes either 0 or 1. Can you see now? It takes either 0 or 1. It doesn't even take value between 0. Okay, if it is, because if it is anything, the decision, this is 0.5. Anything below 0.5 is 0. Anything from there up is 1. So it didn't give us the leeway of having many straight lines, many values, and extend beyond those limits. It didn't give us. And that's why if you are asking a question?
Yes, sir.
Yeah, go on.
So I just wanted to ask, you see this middle graph that your cursor is on?
Yes.
So I want to find out, because I remember that table you showed us that had probability and odds. So I'm trying to use it to describe this curve. You know that there was
this
a
one,
point, like
this one.
Yes, this one. And you know, there are sometimes, even when you look at the 4-figure table, there will be a point that where the values will now be remaining the same. Is that what is happening here? That is, there's a point to reach that, like, okay, if we go back to that curve now, you will see that there was now a point where the thing was the same. Even as the odds were increasing, the frequency did not change. Like, I really wanted to.
Yes, I think it can contribute to that, because if you remember, even the degree of freedom, like all the normal distribution, and that one, you don't talk about the degree of freedom there because it's a standard one. But when you look at chi-square, F distribution, T distribution, all of them, their value depends on the degree of freedom. As the degree of freedom increases, they are close to normal distribution. As you increase the sample size to a level, even they will just be, even if you increase further, it doesn't make any difference. The same value. Yes, I mean, just like even you, it's just like in exam, the highest is 100%. Yes, I mean, no matter. So if you score 100%, another person score 100%, it's because it doesn't really mean that both of you are good at the same rate. Because the scale has already, anything, whatever you get, you cannot get beyond 100%. I remember when we were in when you are them, no chemistry, all this chemistry 101, they are practical. Sometimes, when we do the practical, they are giving, I've learned something from secondary school, right from secondary school, that in mathematics, when you are doing something, is the step they mark, not even only the final answer. If you can, sometimes if you know your step very well, they will be awarding you mark. They even forget that they have already more than the maximum mark for that particular exam, and for that particular mark, it happens. So when they even sum the mark they are giving you is above. So at that point, what they just give you maximum. Yes, I mean, I remember in the chemistry, because I will write the step for the practical, everything the way it is, the raw step, everything. So the people that are marking it, so I score more than the total there. So the issue there is there is a level. If you look at it from here halfway, it has gone to infinity. The examiner. So what is there that even if you increase the value more, it's showing you the same thing. So that's what it means. Yeah, it contributes to what we are saying. So now, now that one also is not helpful because it's skewed. So the intelligent people now say, okay, let's calculate the logarithm of that hot. And that logarithm of hot, the hot is from 0 to infinity, but the logarithm is from 0, infinity is from the 0 side, and infinity on the positive side. Because if you look at it, if you remember, when probability is 0.5, hot is 1, and logarithm of 1 is 0. Yes, I mean, logarithm of 1 is about, logarithm of is 0 point something. Logarithm of anything that is less than 1, the logarithm will be negative. Can you see now? Logarithm of 1 is 0. Anything is 0 point something that is less than 1, it will be negative. Anything that's logarithm or anything that is above 1 point something will be positive. So can you see now? And if you look at it in the normal distribution of something, if you are considering if probability for normal at 50, that would be the middle now. The normal distribution, the middle, 1/2 is 50, the other one is 50, right? So at 50, if you look at the proportion now, if you follow at 50, the middle, when you travel halfway, that would be the middle. So, but if you remember, when the probability is 0.5, the odd is 1, and the logarithm of odd is 0. Can you see? Of 1 rather is 0. Can you see? When you now do log odd, that 0 with that 1, odd 1, which correspond with probability 0.5, the logarithm is 0. Are we following now? Anything odd less than 1, the logarithm will be negative. Anything odd above 1, the logarithm will be positive. So what is there is that from that 0 to infinity on the negative side, and from 0 to infinity on the positive side, it follows normal distribution, but there's no limitation to the value it can assume. Does it make sense now? And that is why it was adopted. So let's continue now. Since logistic regression calculates the probability of an event occurring over the probability of an event not occurring, the impact of the independent variable usually obtained in terms of odd. Can you see now? So if you look at it, what you are actually, when you say you are calculating odd ratio, you want to compare the logic behind all those relatively odd ratios. Okay, what is how many times the probability of the event in the exposed is higher than the probability of the event non-exposed? You can only do that by putting the probability of the event occurring among the exposed at the numerator and the one among the unexposed at the denominator. Can you see now? So also, if you want to talk in the context, okay, the probability event happened over the probability event did not happen, you divide by the probability the event did not happen. It's a form of odds. I already said that. With logistic regression, the mean of the response variable in P, variable P in terms of explanatory variable X is model relating P and S to the equation. This one is just trying to give you, okay, we explain it further down. Unfortunately, it's not a good model. I think we are saying it's not a good model. If you said, okay, the probability that event, because the event of interest, if it's expressed in probability like, oh, either yes or no, other is there or not there. So, and you now say, okay, this will be your intercept, this will be your, you remember this second left side, on the left side of the equation, that is the left side of the normal regression equation, remember. But the other side is not expressed, instead of expressed in y, the value, is expressed in the probability, either it's there or not. So it's not good model because extreme value of x will give a value of y that does not fall below 0 and 1. So the logistic regression solution to this problem is to transform, which I've already said it. So with logistic regression, we model the natural logarithm odd as a linear function of expression. So what you now do is that you now say that odd, which is p all over 1 minus p, you see, natural logarithm ln, natural logarithm of odd down 3 is equal to the intercept plus the regression coefficient x. I don't think if you have a problem understanding the left side of the equation, the right side rather, which is the one that we adopted from the linear regression, which is the intercept plus regression coefficient b and x. But the right side, left side is what we are bringing in, because that is our outcome, which does not follow linear, which will now transform into logit. So when you natural logarithm P all over 1 minus P, that is the logit. So P probability of interested outcome and H is the explanatory variable. The parameter of logistic regression are this alpha and B. This alpha is the intercept and B is the regression coefficient. This is a simple logistic model. You have question concerning this? It's very simple. This model you are seeing now, what differs from the linear model is the left side, which is the logic. Instead of you putting Y, you now do the logic of the that is probability over logarithm of odds, and the odd is probability over 1 minus odd. So logarithm of odd, which is the logic.
Thank you, sir. If I can understand that one.
Yes.
The one we're trying to understand is, I know that I get that X usually is the one that, like in linear regression, I understand its rule. But here, when I was trying to understand what you were saying, that because I know that for that X, for logistic, it would be a yes or no, so it will fall between 0 and 1. So I was trying to understand your explanation there.
No, wait,
about
no.
extreme.
You are missing something. This X here in logistic can be something that is between 0 and 1. It can be any number, the X here. Our problem is the Y. The outcome is the categorical. You know, even in linear regression, we can assume even the categorical we want to use it as explanatory variable, as a predictor. We code it 1 and 0. You remember? So forget about X. X just leave X out. X has no problem. It's the Y. See, the X here is like the X in linear regression. But the Y is our problem, because the Y in linear regression is any number also. The Y here is probability is either 1 or 0. Is that yes or no? And that is yes. And it limits it will not allow you to follow for us to follow linear model very well. So that is why that Y is the one we transform. Since it occurs as probability, we transform it to logic by going through odds from odd to logic. Does it make sense?
Yes, sir.
Okay. There's no other. Let's move on. So, taking the antilog of the equation, you can take the antilog of the equation also, on both sides. One can derive an equation for the prediction of. If you look at it, it's very funny. Well, is it funny? You know, you move from the Y is in form of probability. You change to odd and now change the odd to logic after you finish your work, because it doesn't make sense. Also, you still want to express it in probability bar. You now do the antilog. And the probability you are is comparing, because it's ratio also. You want to now express it as odd ratio. You want to know how many times this one, the outcome will happen among this more than the other group. So all you need to do is that, you have calculated logic. You just do antilog. When you calculate it, will now give you odd ratio. You have odd. Okay. We'll explain it further. Don't worry. Now, it gives you this formula, but sometimes you don't even need to crack your paper. So just understand. We are going to calculate with hand. You go to see. It's so interesting that you get, and we run it, you get the same answer. Extending the logic of the simple logistic regression to multiple predictor. If you look at it, what differs also is that you have B1, X1 to B2, X2, up to as many as possible, just like you have in multiple linear regression, the same thing. And you can, if you want to do the antilog, exponential, the same thing. Now, we have talked about, let us talk about, well, even this one, I don't think it's necessary, odd ratio. Since we talk about probability odd ratio, let's just talk, we understand odd ratio. The odd ratio is a comparative measure. We need to discuss it because our answer will now come out in form of odd ratio. The odd ratio is a comparative measure of two odds relative to the different events. For two events A and B, the corresponding odd of A occurring relative to B occurring is, that is, odd ratio of A versus B, odd ratio of A over odd ratio, odd of A over odd of B, you now divide them, it become odd ratio. And you know the odd of A is probability A all over 1 minus probability A. Everything divided by probability B all over 1 minus probability B. That is the odd ratio. When the logistic regression is calculated, the regression coefficient, which is B1, is estimated. No BO will be the intercept. B1 is the regression coefficient. Is estimated increase in the log odd of the outcome per unit increase in the value of the dependent. If you remember, what you are using here is log odd. So your regression coefficient you get is the increase in the log odd per unit increase in X. I don't think we should have problem with that, because in the linear regression coefficient B1 is increase in Y per unit increase in X. But here we have expressed our Y as log odd, which is logit. So the regression coefficient will be increase in log odd which is increase in logit per unit increase in X. In other words, the exponential function of the regression coefficient is the odd ratio. So for you to actually, what is telling you is that that is B1 mean increase in the log odd all over a unit increase in X. So if you now transform the log odd now, you know it will, from logarithm you reverse it by true anti-log. What you get is that how many times, what you get is the odd ratio among the group that are exposed over odd ratio among the group that are not exposed. Because this B1 was increasing per unit X. So logistic regression is one way to generalize odd ratio beyond two binary variables. What we are saying here is that if it is to calculate odd ratio for two binary variables, outcome is binary, exposure is binary. We don't need all this. We know how to do that. 2 by 2 table, AG all over BC. But when the exposure variable is not even categorical, it can even be more than 2 categories, maybe in ordinal manner. Or it can be quantitative, like age, like blood sugar, just like that. So logistic regression is a way of, that's the only way you can calculate odd ratio for binary outcome and any form of exposure. The one we use in table, it has to be binary outcome and binary exposure. Suppose we have a binary response variable and a binary predictor variable, and in addition we have other predictor variables that may not be binary. So it's appropriate. Logistic curve. So the logistic regression is a method for fitting a regression curve when Y consists of binary code 0, 1 or failure success data. When the response is a binary dichotomous variable X and X is numerical, logistic regression fits logistic curve to the relationship between S and Y. That's what we have been saying. Logistic curve is an S-shaped or sigma curve when you often used to model population growth. The logistic curve starts with slow linear growth followed by exponential growth, which then slow again to stable rate. That's why you see just slow linear, the exponential just skyrocket up and now slow down. Look like X, sigma curve. A simple logistic function defined by formula this. You don't need to bother yourself about this. And to provide flexibility, the logistic curve can be extended to the form where this alpha is intercept, B is the slope. Logistic regression fits. This alpha here is the We will soon call it B0 also. Y is the intercept and P the regression coefficient. So the logistic function is used to transform an S-shaped curve into an approximately straight line and to change the range of platform. So the S-shaped curve you see is the probability, but when we did the logic, it becomes straight line. Give us a straight line curve. So I think I've shown this one before. So the logic, the formula now, I think we are showing this one. And so if you look at it, the alpha is the intercept, which we are going to call beta 0. The beta is regression coefficient, X the predictor. So logistic curve, that is when you plot probability log odd, because the probability against log odd give you this shape. Now, fitting regression. How do we fit regression line? No, remember in our linear something, we talk about how do we fit the regression line in linear model. In our linear regression, we say that we build a model with a straight line, and we use the method of least square to know the best line. Method of least square. But this one, you cannot do that yet because the graph is not like that. But you use maximum likelihood estimate. The maximum likelihood estimate method is a likelihood maximization method, while the ordinary least square used in linear regression is distant minimizing approximation. You remember, because we say in linear regression, it is the line that minimizes the distance between each value and the line, which is the error. When you square each of the error, and you now add everything together, the one that gives you the smallest value, that's the method of least square. That is what we do in linear regression. We call it is a distance minimizing method. But this maximum likelihood method, what it does is that when you have a probability of set of value, look at, we already know that the outcome we are measuring is either yes or no. What we are trying to see, okay, what is the intercept and what is the regression coefficient, both the intercept and regression coefficient, that will give us the best. That is, if people that are anything that the probability is of outcome is 0, greater than 0, will give you 1. The other one less than 0 will give you 0. And less than 0.5 will give you 0. The best intercept and the best regression coefficient that best discriminate between those who have the outcome and people that don't have the outcome. So you'll be surprised. The computer that does it, they use method of iteration. Iteration means they try, is the arrangement. So if we are to do it with time, we have to now do it many times. Use and to calculate. If we push, okay, if we put 30 on this side, I put 30 on this side. How many we have the attribute? How many we not have the attribute? If we are to do it, we may have to rearrange it. It can be put back up. But because computer programming can try simulation 1,000 times within 5 minutes, because program, so it will arrange it, and now give the best. That's what we call maximum likelihood estimation. If you really want to understand it, if you maybe what do we talk about? If you go and read about binomial distribution, you have a clue about maximum likelihood estimation. I think I will, know we have done probability distribution. I will give one lecture only devoted to binomial distribution. You will be able to understand. If you look at binomial distribution, they will tell you if the probability of tossing a coin or doing, if the probability of a disease happening is 70%. Of course, the probability that the disease not happening will be 30%. So if you sample 100 people, can you see what is the probability of the disease in the population? You know, they already give you a value of 70%. So with that population, and you now calculate with binomial, you now say, oh, this is the probability of this. But the likelihood, the best, if you begin to vary this value of 70% to maybe you change it to 80%, calculate the probability in that population. You get to vary the value. The maximum likelihood estimation, the probability you set for having the disease, yes or no, that give the highest prevalence of that disease in the population will be the maximum. I don't know if you understand now. So that is the logic behind it. So what the computer will do, it will set a value of BO and BX and see which one give the best estimate for the outcome. So after you have done the arrangement iteration, you now come with the one that gives the best. We now give you the value of BO and B1. So the maximum likelihood estimate BO and B1, so that plugging this estimate into the model for PX yield a number close to 1 for all individuals who have the outcome of interest, and a number close to 0 for individuals who do not close. This intuition can be formalized using the mathematical equation called likelihood function. They leave that one. Look at what we are seeing here. If the probability, look at here, look at this graph now. The middle one is the threshold value. When the threshold value is 0.5, that indicates, you look at it, you know, we are moving between 0 and 1. Anything that is above, anybody that have the probability above this will be counted as 1, has the disease. Anybody that have the attribute, anybody that have the probability below 0.5, counted as doesn't have, put down to 0. And funny enough, that's how life is. How life is. In exam now, like in medical school, they say that pass mark is 50%. It's like this. Anybody that's just scored 50%, just even above 50%, and the person that scored 100%, all of them pass. So anybody that scored 49.99 that has not meet that 50%, they say it's fail together with person that scored 10%. All of them fail. The same thing. It's not fair. Okay. We'll now quickly look at, if you remember when we did the linear regression, after looking at we try to see how do we evaluate the model. Before we can use the model, well, how will you say this model is good? Oh, that was where we were talking of R squared, talking of the F ratio. So let's quickly discuss that now. After you have fit this, you have fit the model. You know what the meaning of fitting the model, if you remember, even in linear regression, I make reference to linear regression because it's easier to conceptualize, because that's the basis of it anyway. So when you go back to it, you'll be able to understand, because this one is just more like permutation. So that's why I'm making reference to that. If you remember, fitting the model just means knowing the intercept and the regression line. Once you know it, finish. You're able to draw the regression line. It's the same thing here. So after we have used the method of maximum likelihood estimation to fix the model here, how do you know if these models are good? Is there any question before we proceed? Close the door. I've not finished. Any question?
That's a maximum likelihood.
Okay, estimation. Well, it's a little bit tricky. Remember, I made mention of something like that when we were talking about likelihood ratio, chi-square. I said using maximum likelihood estimation. I gave an example now. Let me repeat in another way. If you say that if you want to estimate a disease body in the population.
Yes, sir.
Yeah. You want to estimate the disease body in the population. And you have to take sample of a particular maybe 80 people or 100 people to estimate. If the disease, the burden of the disease is 30%.
Okay.
If you take 100 people or 200 people, 60 will have the attribute, right? Because the body is 30.
30%. Okay.
Now, if you continue taking, of course, you know that for the fact that the disease is 30, does it actually mean that you get 30, the same, exactly the same percentage when you are taking many samples?
Yeah.
So, but by the time you take many samples, we expect that's, if you remember sampling distribution, you expect it to follow normal distribution. We expect that at the end of the day, the mean of all the value you get will be around that 30.
Yes.
Now, if you decide to now take, instead of taking a sample size of 100, you may decide to take sample size of 50 and do the same thing. Taking sample size of 60, you may not get the same answer with taking sample size of 100. Yes, I mean now. If you take sample size of 200 instead of 100,
yes,
you get something. You will get something else. So, for you to be able to actually get the best estimate,
yes,
so for you to be able to get the best estimate, you may need to try many samples. So when you try many samples, at the end of the day, the best sample you choose that give you the best estimate will be it's like maximum likelihood estimation. I don't know if you understand that. It's more like trying many ways to be able to know the one that will give you the best accurate answer to what you are looking for. That's meaning of. So If we are to do it manually, it's very cumbersome. It's just like when we talk about sampling distribution. If you do many samples many times, it follows normal distribution, especially if the sample size increase. But nobody take sample now. In those days, we were doing it too, and it was easy. You know why it was easy to do that? Because they go to Monte Carlo, where they do casino, where they gamble. And you always see people that gamble, go per day, they collect the data there. The same, you know, when you go and collect the data of the same type of game, it's different sample you are taking now, because in a day, many people come, 100 people, more than 100 people can play that thing in a day. And you are collecting the data every day. You are taking each sample of the same type of game. In that situation, you are doing multiple, you can collect many something better. Nobody does that again now, because the intelligent people now discover that because what they wanted to know is to calculate the standard error. You now discover that the standard error is standard deviation over square root of sample size. That is, if you know the distribution of the only one you take now, you know the standard deviation, just divide by the sample square root of sample size. It means that the higher the sample size, the more accurate any estimation. That's how they got to know that the higher the sample size, the better the estimate. The lower the sample size, the lower the estimate. So nobody does that. But in this maximum likelihood estimate, if not because of computer, it will be difficult to analyze. And if you remember, this logistic regression issue, 10, that's language of computer. Yes, I'm now. So computer make it easy for this logistic regression, because that likelihood estimation, try many ways, computer can simulate. Yes, I'm now. Within, I will show you when you want to run it, you show you how provision is made, where provision is made for it, even in the software, when you are running it. So, I forgot. Where did you run it? So at the end of the day, it make it easy to estimate. I don't know if you can get the mental picture now. You just try many. So what the computer does is to fix the value of intercept and B1, different value, and estimate the one that gives the best estimate. Then we're able to say anybody that have anything, the probability of is 0.5 and above, and say that the attribute is there, and the one that is less than 0.5 and below, the attribute is not there. So the value of BO and B1 that give the best estimate, that will be the one you should. And within 2 minutes, that's why sometimes when you are running that type of, if you are running logistic regression, you discover that it's slower than running some other this, because within that few seconds, the computer have made the arrangement up to maybe 1,000 times and comes out with result simulation. So now let's proceed. To evaluation of logistic regression model. Part involved in evaluation of logistic regression model. The overall model relationship, there are 4 different approaches to evaluate it. You can look at the overall model, that is the relationship between all the independent variables and dependent variable. You can look at the importance of each of the independent variables and predict the accuracy or discrimination ability of the model. You can do the model validation. Those are the 4. Likely under the overall model evaluation, likelihood ratios test, omnibus test for model coefficient, pseudo R square, O'Malley short test, all those things you get to understand. If you remember pseudo R, you remember R square, what it does. But it doesn't do the same thing here. It's not as powerful as the linear regression. When we talk about the likelihood ratio, it measures how poorly the model predicts the outcome. You remember in linear regression, we talk about because this model predicts the actual factor very well. This one measure how poorly it predicted. There's something I say I wanted to go over and show you here. What it does is to do minus log, like they call likelihood ratio. It's always -2 likelihood ratio of the norm model minus 2 likelihood ratio of given model. What we call norm model here is if there's no, if you remember, the intercept is the value of y when x is equal to 0. When there was no x, y has value. It's the same thing here. The intercept is the value what the model predicts for the outcome when there's no independent variable. The independent variable is not there. And this is norm model. That is the norm model. That is the one that corresponds to the mean. Remember, in linear regression, I said the crudest model you can only compare with is the mean. And mean is when no hypothesis is true. When there's no difference in the value of this thing, there's no change. That is norm. So if x does not make any difference in the life of y, it's like as if x is not there. And when x is not there, what is the value of y? That is the intercept. So you see, it's a little bit tricky, but while it is usually negative, is a likelihood fall between 0 and 1. When you say likelihood, likelihood means more like probability. Likelihood is in between. The probability between 0 and 1. So, but we are dealing with log here, logarithm. No, here we have brought in log. And log of likelihood of less than or equal to 0 will be minus. You know, remember the log of is or 1 is 0. So if you are looking at log of anything between 0 and 1, it will be negative. Because we have already said that log of 1 is 0. Log of anything less than 1 is negative. Log of anything greater than 1 will be positive. So what we are dealing is between the outcome is 0 and 1. So the log will always be negative. So if a model has a very low likelihood, then the log of the likelihood will have a larger magnitude to the log of more likely model. So a small ratio of the log likely indicate that the full model is far better. So what it just does here is that this first log likelihood here is the one just talking about what the model is when x is not there. Then when you have added x, is this likelihood given for the model. That is the model. So the difference, what difference has he made? That's all. And it can be another, in another book, you can write it like this, you can write it like this, it's the same thing. You either say this minus this or log likelihood of this one over this. This way I want to demonstrate it. At least you have a mental picture of it. I will encourage you normally when we do it next week also you come back and so that you solidify your this. Look, I said something yesterday. I just stopped here. I did when I was sharing, explaining this slide. I just said, let me just stop. I'll come back because I feel this is where it is needed. You know, one thing with logarithm scale is log of the difference between two log is the same thing as the log of the division of a two value. That is logarithm of A minus logarithm of B. The same thing as say you divide A and B and find the logarithm. For example, if you choose 6 and 2, you have log of 6, you calculate it, and you calculate log of 2. You remove log of 2 from log of 6. It's the same thing as say you divide 6 by 2 and do the log. Look at it here. You know, if you remove 2 from 6, it's 4. But if you divide 6 by 2 is 3. So logarithm of 6 minus logarithm of 2 is like you are doing logarithm of 3. It's not logarithm of 4. Look at it. Look at this table here. Sorry. It shows the logarithm, the number from 1 to 20, and their logarithm. I just generated this. Excel. I just say, okay, what is the logarithm of 6 here? 1.79. What is the logarithm of 2 here? Is 0.69. If you remove 0.69 from 1.79, that you are removing logarithm of 2 from logarithm of 6, it gives you 1.10 if you do it now. But go to logarithm of 3, 1.10. Logarithm of 4 is 1.39. So you cannot just say you cannot say logarithm of 6 minus logarithm of 2 is equal to logarithm of 4. No. So that is the relationship between normal scale and the logarithm scale. So that was why that formula is in some book. If both of them are correct, you either use this first one or use this one. The reason, because the log likelihood here, you have calculated log likelihood separately for this one, you log likelihood separately for this one, you remove it. Or you first of all divide this and this one, likelihood of this and this one, before you calculate the log, it gives you the same answer. So I think let's move further because I envisage that this one will be easier for you. The omnibus test is actually a chi-square test. It gives the result of the likelihood ratio test, which indicates whether the inclusion of this block of variable contributes significantly to the model. What he's saying now is still explaining this other log, like the likelihood also. That is because you're going to see the computer, we are going to generate, calculate some of this thing. When we run it, we're going to see it. The explanation will make more sense when we run it. So what this one does is that before you bring X, what is the result we have? We know that before we consider the effect of X, we can see the value that, oh, out of the total, this is the number that have cardiovascular disease before we even consider the effect of X. When we consider the effect of X, what does he have to read in predicting those who have cardiovascular disease? That's what this one is doing. They test the null hypothesis that the adding the independent variable to the model has not significantly increased prediction of the outcome. That is, adding subsequent independent variable, even the first one, even the second one. What does it have to read? A value of less than 0.05 for block means that the block one model is a significant improvement. Of course, it's a normal thing that when the p-value increases, it means that there's a significant addition. So the other one is pseudo R. This one sounds like the R, the other one, but it's not as powerful as the R square. So why they call it pseudo R square is that something like R square. Because you cannot, the reason is very simple. You cannot calculate correlation the way you calculate correlation down. Because if you, the R square in linear regression is related to correlation. And since you can't calculate correlation here, some people just, intelligent people just use some mathematical manipulation to work something out. They think they're doing the work of R square. And that is why they call it pseudo R. So there are many different, in fact, more than the SPSS show you these two, called Kasne R square and Nagereke R square. There's another one, McPherson R square. There are many people that describe their own. So different type for different people. So the only thing that cause and snare R square can be interpreted like R square in a multiple regression bed cannot reach a maximum value of 1. No maximum value of 1 means that 100% cannot reach. The Nagereke can reach 1. Now, the homolemation. This one is a form of chi-square that uses to examine whether the observed proportion is greater similar to predicted probability of occurrence in subgroup or model population. It is performed by dividing the predicted, you go to see the predicted value into 10. I will show you in the expresses how to bring the result out. You divide them to 10 groups, rank them, and look at observed and the predicted value. And now observe minus expected square, use normal Pearson chi-square to see. It follows a distribution. The degree of freedom is usually 8 because there are 10 groups minus 2. The degree of freedom is usually 8. So small value with large p-value closer to 1 indicate a good fit. So this one is in opposite direction. It is when it's not significant, you say it's a good fit. If it's significant, that is what it means that if the difference between the observed and the predicted is not much, it's a good fit. But if the difference is much, it's not a good fit. So when the p-value is less than 0.05, it's a poor fit. But the people that invented we do not recommend using it to test when there's small sample size, like less than 400. So the statistical significance of individual regression coefficient. So I think we are getting closer to the one you may be able to conceptualize better. The same likelihood ratio test you can do. Then word statistics. This word statistics. Though this likelihood ratio we are talking about can do the same thing also. Because what it does is there any further improvement? Then the word statistic, I've been making mention of this word statistic even before. When we talk about chi-square, I say it's a form of chi-square. Though we show you is presented in 2 ways. If you run, if you walk, if you use epi-info, when you run logistic regression, it presents what statistic as Z. Z means that it follows normal distribution. And what is there? How do you get the word statistic? Look at the formula that the beta, that regression coefficient divided by standard error. You just want to know how good is the model to the coefficient you are estimating. Because the meaning of standard error means that for that your sample, if the standard error is very big, it means that the estimate is not precise. If the standard error is very small, the estimate is precise. It will be closer to the parameter. You know, whatever you are doing with your sample is statistic. That beta, you calculate a statistic, that regression coefficient. Then if it is the whole population you use, not sample, it will be parameter. So how close is this beta to the parameter? When the standard error is very large, it means that this beta will be far from parameter. If it's very small, it will be close to the parameter. So what the word did to divide the beta by the standard error. When you divide the beta by the standard error, that thing follow the normal distribution. And that is what some software present, like epi-info. But some, you can square it. When you square it, it follows chi-square distribution. And that is what is presented in SPSS. So when you are doing your logistic regression, you may see Z somewhere, you can see chi-square somewhere. To do or they call it word. They can call it word bet. You have to. So in chi-square, in SPSS, it is square. When you square beta all over standard error square, that's the chi-square. When you don't square, that is it. You remember in our lecture on chi-square, the first time Pearson described chi-square. How did you do? He square Z, normal, standard normal. He square the standard normal deviate. Now discover that it follow a pattern with particular distribution. I think I made mention of that even when we were discussing chi-square. Odd ratio with 95% confidence interval. That is one thing we do. We're going to see how we do that to translate that beta. You know what led to that beta? You know, we have already said that beta is increase in log hall per unit increase in the x in independent variable. Increase in the log hall per unit. So if you, since it's log, calculate the anti-log, which is the exponential, it gives you the odd ratio. Now, the other thing you can do is to do cost tabulation, and this one also is in the SPSS. When you do cost tabulation, the classification table. The classification table is a method to evaluate the predictive accuracy of the logistic regression model. In this table, the observed value for the dependent outcome, the predicted value, as a user-defined cutoff value, and cost classified. For example, if the cutoff value is 0.5, which is usually, I will show you where that is set also when you are running it. No, I've already said it, because the output is 0 or 1. So anyone that's 5 above classified as 1, 1 below classified as 0. So the predicted value above 0.5 can be classified as predicting an event, and all below as not predicting event. Then a 2x2 table of data can be constructed with dichotomous observed outcome like this. So we're going to see it. Maybe when we see what will come back. Well, it may not make sense me explain this table now. But when we run it, I'll come back to this. I'll compare it with what we see in the SPSS. Discrimination with ROC curve. You'll be hearing of deceivers operating sizes. You know, I'll be looking forward to the time we do diagnosis tests, and you know, there are a lot of things that are so interesting in statistics. We are in an environment where people just want to remain mentally docile. Mentally docile. You see, we keep on blaming our government. It's not the problem of Africa is general. It's not only government. It happens that the people in government, they are African like us also. The people in the hospital, they are African like us. In different parts of the economy, they are African like us. Then we try to say that it's only the government. No, it's not only the government people. So nobody wants to think very well. So the receivers operating will still do if possible, because I have already made up my mind that, because I was thinking before that I will do this workshop before the year runs out on receivers diagnostic text where we plot ROC curve. I've done the training. I think it's only, yes, I've done it in a couple of times. We are in Port Harcourt. So rather than selecting a single cutoff, the full range of, instead of creating a full range of cutoff from 0 to 1 can be examined. For each possible cutoff value, a 2x2 table can be formed. Plotting the pairs of sensitivity and 1 minus specificity on the scatter plot provide the ROC, which is the receiver operating characteristic. So we will not go into the detail. It is in that type of training, the logic behind it is explained. The area under the curve provide an overall measure of the fit of the model. The area under the curve varies from 0.5. That 0.5 is the gambling, you know. It's just like if something, just like you toss a coin, say that is 0.5, the head is 0.5, not head is 0.5. If something, the predictive capacity of something is 0.5, it doesn't make sense. It's like gambling. So it's really from 0.5 to 1, perfect predictive ability. So the larger area under curve indicate better predictability of the model. Point above the diagonal dividing the arrows represent good classification result, better than the random, while the point below represent poor result, worse than the random. So because the diagonal is 50%, don't worry, you cannot conceptualize very well. There's no problem. It's bit by bit. So the last one that the evaluation is, you can just evaluate what this one just means. Is just to evaluate. And evaluate just means that we did that in linear regression. When we finish the regression, we now choose a value out one particular. Remember when we predicted the pulmonary dead space from the height of the child, we now choose one value of height and now try to calculate the pulmonary dead space to see the difference and try to estimate even the R square from there. Remember, it's the same thing, but it is recommended that actually, if you want to do that, use another data set, not even that one. Use a particular data set or somebody that have measured the pulmonary dead space and they also know the height. Try to predict it and see if it does it very well. Because if you do it with the one you have, like the one we did, yes, it's internal validity. But the external validity is maybe questionable. But if you try to use other data set, that will be external validity. So, and that's what we call generalizability. So it's done by deriving a model and estimating its efficient, its coefficient in one data set, and then using this model to predict outcome variable from the second data set, then check the residual. We did that when we were doing this thing, linear regression. When a model is validated using the data on which the model was developed, it is likely to be overestimated. That is, it may give the impression that is good more than how much it is good. So the validity of the model should be assessed by carrying out tests of goodness of fit and discrimination on a different data set. You use different data set. If the model is developed with a subsample of the observation and validated with the remaining sample, it's called internal validity. That is if you do it with part of the data and then validate with other data part, internal validity. So that is why they use different methods like splitting. You can split data splitting. You get much understanding of this if you do reliability and validity. One of the method of reliability is splitting. You've heard of split half reliability coefficient, Cronbach alpha. Data splitting, repeated data splitting, jackknife technique, and bootstrap. If the validity is tested with a new independent data set from the same sample or from a similar population, it's called external validation. That's external validation. Obtaining a new data set allows us to check the model in different contexts. If the first model fit the second data, there's some assurance of generalizability of the model. However, if the model does not fit the second data, the lack of the fit can be either due to the different context of the data set or true lack of fit at the first model. So lastly, before we go and solve the problem, let's look at the assumptions. You know, in the linear, if you look at something here, it appears that in trying to validate the model, we have many things in logistic regression now, linear regression. It's very understandable because the concept grew from the linear. So, and most of these things easier with a quantitative variable. So, for categorical variable, if care is not taken, you may be doing the wrong thing. That's why there are different ways to validate to make sure that you are not bringing a wrong result. That is why you have too many things you need to do, because the concept, the idea is originated from the quantitative balance. We're trying to use it for categorical outcome. You need to do a lot to validate it. So major assumptions. You know, like in linear regression, we have assumptions. But all those assumptions in linear regression, they are not tenable here. They are not needed, but there are some that are still common among them. The dependent variable should be categorical in nature. You already know that. There should be no outlier in the data, which can be assessed by converting the continuous predictor to standardized score and removing value below minus 3.29 or greater than. You're still talking of the standard deviation now. If you do the z-score, or you convert it. So you are trying to see if you explore the data, the predictor, not the outcome now. You are trying to talk about some predictor, there should not be outlier. And it's very simple. You know that originally the outcome is between 0 and 1 anyway. We are just trying to do logic to make it open. Still, if there is extreme outlier, even the linear regression outlier affect it. So it will affect this one also. So if you explore the data, you see, you look at the skewness, you can actually know the number of standard deviation away. The standard deviation. Then there should be no high correlation, multicollinearity. I think we have talked about that one also is tenable in non-linear regression. Two variables should not correlate perfectly. No, we are talking of those exposure predictors now. No, you can use the predictor the way they are, either they are continuous or categorical or whatever. This can be assessed by a correlation matrix among the predictors, which we did also for linear regression. We first of all did correlation matrix to see. Then some of the giants in statistics, as Tabasny and Fidel, suggest that as long correlation coefficient, so that as long correlation coefficient among independent variables are less than 0.9, the assumption is met. So when we are talking of collinearity, you know, when the correlation is becoming more than 0.9, it's close to being perfect. You know, perfect collinearity. It's close to once it's more than 0.9. But if it is less than that, yes, the assumption is met. So the last thing here, I keep on saying, there's tendency to overfit. When selecting the model for logistic regression, another important consideration is the model fit. Adding independent variable to logistic regression model will always increase the amount of variance explained in the log, typically expressed by Hausfeld. However, adding more and more variable to the model can result in overfitting, which reduces the generalizability of the model. You can perfectly fit, which is not actually good. So when there's a perfect fitting, it's easy to have perfect fitting with logistic than linear regression. And it's very simple. A situation of perfect fit is that all the people that maybe you are trying to look at the issue of this obesity and cardiovascular. If all the people that have cardiovascular disease, they are obese, and all the people that don't have cardiovascular, they are not obese. That's a perfect fitness. Just a crude example. So it is easy because the logistics is more like arrangement. This side, it belongs to this side. We can't belong to any other side, any of the two sides. Unlike linear regression, that is not a matter of that. The outcome variable can take any value. So you are not divided into any two groups. So here that it just they arrange everybody into either this or this. So you may have problem with that perfect. I think let's look at the example of that obesity, cardiovascular disease. This is the data. Here now we are looking at the data generally. Is there any question before we go? Before we look at the data and solve it and run it? We do that. By tomorrow, we now use data that have multiple, can do multiple linear with it. Any question before we proceed? No question? Are you following? Hope people are not sleeping.
We're there, we're there.
Any question?
We're
following, sir.
Okay.
We're there.
Okay. It will be easy. Most of the time, say there is no, unless it is when we run it now, the shock will come up. Yes. Sorry for the long, there are too many things about this logistic to iron out. Unlike, it's not as straightforward as understanding it like linear regression, but when you get to know it, it's straightforward. The interpretation of the result is easier. You can be sure of that. It's even easier than the linear regression. I'm telling you, it's try to understand the concept. Concept may not be as straightforward. Okay, let's look at this now. This is a data set for the obesity and cardiovascular disease, and the total number is 1,000, out of which 300 are obese, 700 not obese. 106 develop cardiovascular disease, 894 did not develop cardiovascular disease. Now, if you are to calculate odd ratio here, you just say 466 times 640, which we did yesterday, divided by 254 times 60. It will give us the odd ratio. With the crude odd ratio, we got a 1.93 yesterday. Through that, very straightforward. But why all these problems? Because this data set is simple because both outcome and exposure are dichotomous, binary. But we need to understand the logic, because the way we calculate this one now, when the exposure is continuous, you cannot do that. It's not as though you cannot even use this one to calculate it. And that is how intelligent people came with this issue. That's why this regression issue comes. So, I said earlier the other time that it is the logistic regression that allow you to calculate odd ratio for both the binary and non-binary, for association between binary outcome and exposure that either binary or non-binary. Can be continuous, can be anything. It's through regression you can do that. And though to understand it also, for you to understand the basics, it's good to start with how does it work for binary and non-binary. That's what we want to do here. Applying the logistic regression model, which we have described, this, you see the left side is the whole, is the logarithm of the hot, which is the logic, which is natural logarithm of P over 1 minus P, which is the logic. And the left side is what you see here is the intercept, and this is the x and its regression coefficient. So the right side of this equation is the same thing with linear regression, but the left side is the log of instead of y in its natural state. The y is coming up as logarithm of odd, which is a logit. For obesity now, if you want to really know, want to see, fitting the model. Once you want to fit the model, what you do is what is the value of the intercept and what is the value of the regression coefficient. The intercept, if you apply this formula now, the intercept is B0. You already said it can be written as B0 and the other one B1. So the issue there is okay, there's one, okay. If there's a step here, which maybe I didn't put, even when there's nothing at all, that is, there's no x at all, there is a value. Of course, now when you put y, that is the intercept. When you put y, and when you put x rather, you now have the intercept together with the b1. Now, you have to, because you have coded this thing 0 and 1, so you write the equation. If you remember, when I run linear regression for that lady's data on peak expiratory flow rate, when we were writing the equation, we have to write separately for male and female, because that was the only categorical outcome there. You have to write it really separately for male and female. So it's the same here. So and in that one, when you have two categories, one will serve as reference. So no obesity is reference here. For obesity, it's got to no, which is there's no obesity. The value is O. So if you write it, you put what is the probability of the disease. Look at it. For obesity, no. The people that have yes, the disease 60 over the 1 minus p, that people that don't have 640. Can you see? That is logarithm of 60 over 640 will be equal to this part of the equation. And in this case, the value of the x is 0 because the value of the obesity is 0. So that's a B1 times 0. That x is 0 here. Now, if you use your calculator, now I use Excel, I'll show you. You use your calculator to do 60 over this thing and calculate the log. It will give you this. So I think I will, okay. Let me just explain it. So when you now put it now, if you have doubt there, we can do it together with Excel. Instead of you, because for you to get log now, you are need scientific calculator, but Excel actually give it to you. So for you to get a log. So 60 over 040, the logarithm or natural logarithm is minus 2.3671. So since this one is 0, 0 times B1 will be out to be 0. So it remains this. That shows that the intercept is minus 2.3671, approximately minus 2.367. That's the intercept. Now, for obesity is equal to yes, that is 1. Look at it. How many have the attribute CVD? 40. Sorry, is it 45 or is 46? 46 I get. The mistake is when I was writing it. Sorry. Let me correct it. It's 46 that is there. No. 46 over 2 around 54. No, the value of BUI is 1 for the obesity is yes. So the logarithm of this is this minus 1.70869 BO plus P1. So in that case, if you substitute now, because we already know P0 here, you now substitute here. Now, if you move it to there, it becomes plus. When you try to, when you remove this one, it gives you this. So the answer, the B1 is this. Approximately 0.65. Now, if you run it now, you're going to run it. The B1, B0 will be this. The B1, the intercept for the something will be this. Now, because what it means is that for anybody that is obese, when somebody is obese, the log hall of the cardiovascular disease will be 0.658. So increase in the log of per unit by a person that's obese. So the interpretation is cumbersome. It's not like the linear regression where you say that for a per unit increase in y, x, this is y. The regression coefficient. That is, if the x, the exposure increased by 1 unit, this one will increase by this. It's very simple. So since it's like that, so since you have calculated the outcome occur in probability before. So you now go back. So you just want to know, okay, the odds of having the cardiovascular disease among the exposure divided by the one among the people that are not obese, among the obese people that are not obese. So that you know that how many times people that are obese are more likely to have cardiovascular disease. To answer the question, just calculate the anti-logarithm, that is exponential. When you calculate the exponential for the constant, give you this. For the P1, give you this. Hope I didn't solve it. I solved it, sorry. The constant is this other one, is this. The constant is 0.09. It was the B1, that is this. Let's check. So I think let's run it before other discussion will come, because let's run it. Or which one? Do you want us to go into Excel how you can compute this thing, or we run it first? It's your choice. So we go and run it now with the computer, and let's see the output from the SPSS. Or you want to validate?
Yeah, no need for Excel. No need for Excel.
Is that a consensus opinion? Any other person can talk. Hello?
Yeah, we don't need Excel, sir.
Okay, thank you. Okay, so somebody should run it then. Who will share? Dr. Ogo. Dr. Ogo. He's not there. Maybe he has gone, and he appeared 2 times, so he appeared on Dr. Ogo. Okay, let me use my own. So, look at the data set to analyze regression, logistic, CVD, logistic, you know, the one I've coded, obesity. Now, what I wanted to show you, if you go to options, you will see this one, classification plot, all this one, normally they are not, all this one, none of them is checked. And most of the time, if you don't just run it like that, it will not give you the odd ratio. I usually come to check, but for the purpose of our class for explanation, I'll check this little measure also. So this is what you need to check. If you want to know iteration history, how many times try? Because I said that it's by iteration. You click that one. Then you click odd ratio. You need, because it will just give you, it give you exponential. It will give you it will not give you the confidence interval. If you don't click this, it will not give you confidence, because it's confidence interval of exponential B odd ratio, 95% confidence interval. So if you want to change it to 99, but it's 95 we use. If you look at it, entering. So okay, calculation cutoff. What is in that? Since this is between 0 and 1, it give you, that is, the cutoff point is anything above 0.5 classified as 1. The person have the event. Anything below doesn't have. So maximum likely iteration, how many times will he try to make effort? Usually put when you can put, if you put more time there, it may slow down. You may not get your result on time. Now, okay. Because wait, let me, just wait, I will run it, because I run many things, let me first, so that I won't have problem. Close this something and rerun it, so that I won't have problem looking for the result, because I have too many things. So let me share the result now. Look at it. So 100, you know, the sample size is 1,000. Then look at the beginning of the block. What it usually does at the beginning is okay. Without, it did not include the X. Just say okay. If you say CVD, the outcome. How many have CVD? There are 106. How many didn't have? 1894. So then this is the one that I said I didn't put in the calculation, I didn't put there. What it does, a logarithm of this 106 log of, that is 106 divided by 8. The probability that it is there 106. Probability that is not there is 894. 106 divided by 894, logarithm of it, it will give you minus 2.132. Now, that is when X is not there. It's a variable not in the, it didn't put X, obesity there. And block 1 now, that's when you put the obesity there. And yes, put the obesity variable there. So this is omnibus test of the model coefficient. The funniest thing, if we run this thing now, let's run normal. What is telling you this omnibus test is the step block 1 plus 3, by the virtue that is significant, means that by bringing this in, there is an improvement. the X has brought in predicting the people that have cardiovascular disease. This value you are seeing, this chi-squared here, is the same thing as likelihood ratio, though it's try to take the likelihood ratio chi-square. If I run the chi-square for you now, let's look at the data. Let me just run. You just do cross tabulation, the normal chi-square, cross tab. Are you looking at me? Obesity and CVD. Let me remove this one. I'm not doing maintenance now. I'm not doing relatively. I just want the chi-square. We see. Look at the result. Can you see likelihood ratio chi-square 9.559? If not the same with the other one, it's very close to it. Can you see? 9.559. Can you see? It's the same thing. So it's looking at just like what likelihood ratio the chi-square will look at relationship. So you may begin to ask, why can't we use why do you do regression? Then why can't we use the normal tabulation? But you know we have already said that whenever we are dealing with, if we now come to a variable that is not categorical, logistic will not, chi-square will not do it for you. The logistic is the answer. That is the only reason you do that. You will have just done normal cross tabulation, it will solve the issue, but in a general way, number one, you want to have multiple variable, and some of them, two reasons, multiple variable at the same time, some of them will not be categorical variable, that will be the exposure. So you can see the likelihood ratio also, but this one is a little bit dicey understanding, because you know when I was struggling to explain the likelihood ratio. Let's see if we're able to do that, we know it better tomorrow. But look at the R square, pseudo R square, the cosas and the macre. You can, what this one is telling you is that the R square is only 1%. This one is 1.9% here. No, we already said that this cos and net R does not extend to Y, doesn't have reach maximum of 1. This one is maximum of 1. So it gives the impression that this now get Kerker may be better. But it doesn't make sense. It's difficult to interpret it like normal R square for this thing. Look at lemma shock. This one, we already said before, if it's significant, it means that the thing is not good. But if it's not significant, here, it's not even giving us any something. For the fact that the chi-square is 0, means that the p-value will be 1. That shows that it's a good model. Now, convergence table, okay. I showed this convergence table. That's how the lemma shock calculates its own. The exposure, why is the predicted and expected and observed? If you look, it's the same. That's why the chi-square is 0. The predicted and observed is the same. It's not all the situations like that too. Maybe by the time we run some tomorrow, you'll see. Look at the classification table I talked about. This classification table will show you that okay, this is no. How many people? Yes, that is it. How many people that are no that the logistic that did not develop that you observe that did not develop the attribute cardiovascular disease? How many did the model predict? Say this. Can you see? Then how many is it are in this place also that say yes here, that the model say yes, it should be this one. So at the end of the day, the right prediction is, you know, here is 100%, yeah. When you now put it over total, this is one that is rightly predicted, but this one is wrongly predicted. So when you put this one all over, total I give you, which is 300, to give you 89.4. So the variable equation, the real coefficient, you see the constant BO, which we calculated, minus 2.367. That wasn't on the value we got. Are you following? If you are following, let me know, please. God, Zoom can be taking tea now. Are we following? If you are following.
I'm following, sir.
Yeah.
Yes, sir.
Yes.
So if you don't remember, the constant, what we calculated on the other side is minus 2.367. And this is for the constant. For B1 is minus 6. If you remember, it's 0.658. If you remember. And when we do the log hog, the exponential, it gives us 1.93 for B1. B0 is 0.094. You remember? And this is the confidence interval of the odds ratio. It shows that it's significant. You know, this is the same data set we use for stratified analysis. I remember the odds ratio also for the crude odds ratio was 1.93.
1.93.
1.93. Where in that one, I think the odds ratio should be the same also in that one. And the confidence interval. It is a confidence interval. So if we do multiple, I can go and add the age to it now, which is the adjusted one now. Can add the age. So you will see that it is easier to even do the regression with multiple than just say you are doing stratified. So I don't know if there's any question. This Joshua. Is there any question? Any question?
No.
So all this one, you actually all you need to do is to know how to the way to go around it. But it's good if you come for workshop, you should be able to understand some logic, some science behind it, make you to appreciate it better. And the worst statistic we are talking about, if you put,
now hello.
Yes, sir.
Hello.
I'm listening, sir.
Here the item displayed, there are too many. So when we are to report, which ones do we pick? Because they are
Thank you. We don't report more than yes. For you don't even report. Sometimes you can report almost everything this table, this variable, but sometimes we just report significant odds ratio and confidence interval. These last 4 columns.
Okay.
Only if it is people that know what they are doing, you don't even need to report the significant because the odds ratio, the confidence interval will tell you if it's significant or not. But if you are in an environment where many people they don't understand even how to interpret, they still want to see the p-value. You have to put the p-value there also. But sometimes also, me, I would like you to report from here everything. You know the reason on this table. So people tell lie. This way, because sometimes if something is not significant, they can even change it and change the value. But if I have the value, go and do antilog of 0.658. It will give you the odds ratio 1.932. The exam now. So some people that don't know, if you bring the exam now, maybe you have shared one of the figure here. I will just do the antilog of this to see if the odds ratio is the same. Right. So I don't know if you understand me now. So if you want to see, okay, let me just share my Z 0.658. Let me just share my Z so that because some of these things is you either see it, appreciate it. So okay, O is 0.658. So if you want to do the antilog, it's equal to first is equal to in a cell. You say function exponential is the antilog expo. When you click, Now say which one, you now click on that cell, say okay. What is the answer? Can you see it? What's the answer? 1.93.
1.93.
So that is the odd ratio. So exponential antilog of that regression, B1. So that's just it. So if I show you this one, look at how I generated, remember. If you remember, the overall 185 have the attribute, 115 no, 185 have the okay, no, it's you know, it's not that one. It's not that one. It's another. Oh, it's another data set I put it. Yes, another data set I put it. Another data set I put it. Is this okay? Well, if we are to do that one, yeah. Because so that you can appreciate, okay, what I was copying. Yeah. So if you go to our data set, you see that can we see? Can we see that if you look at the...
No, it's not there.
Okay, no, sorry, maybe I didn't share.
No, it's not there.
No, sorry, I didn't share. You can see, right?
Yes.
See? Yeah.
Yes.
Yes, okay. Now, if you see, the total that have this is 106, and the people that didn't have the attribute is people that total that have CVD 106. They have cardiovascular disease. The people that didn't have is 894, right? The people that are obese that have it, they are 46. The people that don't have it under the obesity is 254. The people under the people that don't have obesity, the people that have the attribute are 60. The people that don't have it is 640. You know, when you're talking of the log, you are not using the total because if let's say you are calculating the probability now, you'll be using the total, but here you are calculating the odd. Odd is the people that have the attribute divided by the people that don't have the attribute. Yes over no, not yes over total. I don't know if you understand me now. For these people that have obesity now, it's going to be 46 over 254. That will be the odd. For this one, I don't have obesity, it's going to be 60 over 640. For the total, it's going to be 106 over 894. That's the way it works. So I just want us to have before we close, because tomorrow we'll be looking at so that you can go and try with your hand. Tomorrow we'll be looking at the multiple logistic. So look at, I've shared, oh no. Did I share the Z? Can you see the Z?
Yes, sir.
Okay, I wanted to be sure. You can see the Excel. I share the Excel now. So imagine I want to just do something very interesting. So I want you to go and do it when you get home. Calculate this thing. So among the overall, the people, if you remember, the people that have the disease, they are 106. The people that don't have the disease, they are 894. Yeah. So the odds will be
106 over 894.
Thank you. Divided by 894. Divided by 894. This is the odd. the hall logit, the log of hall now, you see it's equal to, if you look for the function log, and it's a natural logarithm, say okay, and now click on that odd, say okay. Can you see? It gives you the natural log. Natural log. That is when you are not even bringing the overall now. You have not, just like the way we did the crude yesterday. So yeah, you are not talking of the exposure. You are not talking of exposure. That is, this is naturally safe when there is nothing like exposure self. This is the value B0 for that thing. I will show you. Can you see? Minus 2.132. Okay, now
0.5.
What do you say, sir? And if you do the exponential, of this one, it will, of course, it will revert you back exponential or anti-log. Of course, it will revert you back to the hard here. The hard here. Yes, do there, yes. Look at it. Exponential of this. Can you see now? So I want to show you something now. In the output we did, when the first thing it came out, can you see? See block 0. Can you see? Look at the constant, minus 2.132.
They are not seeing.
Oh, sorry.
Not shared.
I didn't. Oh my God. I thought I shared. I just look at it.
It's not shared.
Can you see that? The output. Can you see? I'll share it. Can you see it? Can you see the output?
Yes.
Yes, we can see it.
Look at.
Scroll down.
Initially.
Scroll up, brother.
Yes. Let me show. So the block 0.
Okay.
If when you first run it, it gives you block 0. Block 0. It has not included in that block 0. It has not included the obesity, which is the hardcore mesh, the exposure. It put is a constant step 0. Constant. The regression coefficient is 2 minus 2.132. And look at the odd, 0.119. You know, remember that was 0.118 something, which is approximately 119. So it's just telling you that at the natural level, that particular 106 out of 1,000 that have the you are not regressing anything. It just you are not bringing the exposure. Yes or no? It's telling you that this is the way naturally it is. So the way to calculate is you just say you ROC all over the remaining, which is 894. The remaining to complete 1,000, 894. It gives you this 0.119. Then when you calculate the odd, it gives you minus 2.132. Now, if, let me share the Excel again. If you now decide, okay, now for the exposed now, if you know for the exposed, not exposed rather, starting with now obesity, is 60 that have the attribute from our table, and 2 that don't have the attribute is 640. Yes, I mean now. So if you extend the odd of that will be this, and the log odd will be this. And just leave this one. Now, yes, if you remember, that is what we calculated, because for the noise, that is now what we calculated as the B0. You will remember our B0, the value you are seeing there, what we even calculated with and what I calculated with, and look at it. I think I've shared, you can see my slide now. If you remember, obesity, no. Can you see?
No, it's not shared. It's not shared. It's not shared though.
Okay, no problem.
It's not shared.
No, I'm coming. So it's here now. Can you see it now?
Yes.
Can you see the value? That's what we calculated. Can you see what I calculated here? Minus 2.367. Right? That is where obesity is no. You know, when the obesity is no, that shows that the value of coefficient B will be 0. So what will be the intercept? Minus 236 this, and that is what you see under the constant in our output. Yes, if you look at the output, when we now put the block now, can you see minus 2.367? Can you see minus 2.367? So I think we just stop here. Any question? So tomorrow we'll continue. So we'll continue, and we now send to you that have multiple logistic regression. We run it. I have a data from Titanic. Those people that were in Titanic, I have the data. We run it. Titanic, because they got the information later, even their name and everything. You know, later in 1913 they got the information. So some parameter about how many people that survive, people that didn't survive, their sex, their many, their class, those with their social class, upper class, lower class, how many survive. So we'll run it logistic. We'll do that tomorrow. Multiple logistic. Any question? Any question?
We just need to let's digest it. We took quite a large chunk of things. Let's digest the clock.
Okay. No problem. Any other? No question, right?
Well, no, I have a question, sir. That's okay. I think we have one that the odds ratio is 0.119.
119.
So, yes, in reporting, how do we?
And that one actually okay.
Yes.
That one, if you look at it, that one is just, you know, when it's effect of programming. Yes, I mean, yes, just giving you that one. That one is just telling you when you have not even put in any the independent variable. This is what you are seeing in the data. Because you look at it, that what if you look at it, that's what I run here. Look at it now. That 0. Look at it now, 0.1185. That is the 0.119. Yes, I mean now. That is the 106 out of the 1,000 that have the attribute. The 894 they don't have the attribute. We just divide the this over this and do the odds, which is 0.119. Yes, I mean now. If the overall, that one you have not brought in the
any exposure.
Exposure. You have not brought in exposure. It's just a description. So when you are reporting, you don't even report that type of thing. I don't know if you understand me. That's why I say the block 0. So the people that do the program just put it there for you. You know, it's just like scientific thing. If the way it was done, you want to put the step there so that for people that are intelligent to logically, see the way it goes. I don't know if I've answered your question.
But assuming that there was, we found this after the exposure, how would we report that? Would we say that 0.
You find after that. The one for after the exposure is there now. Let me go there. The one after the exposure.
That's the last.
Just assuming that it was 0.119. How would we report and put?
If the odd ratio is 0. Yes. What it means is that the people that are exposed are less likely. Once the odd ratio is less than 1, that shows that the people that are exposed are less likely to have the disease. Yes, I'm now. It is when it's greater than 1 that they are more likely.
So would we say that they are 0.119 times less likely to?
No. You just say, people say that if you want to know how many times you calculate the reciprocal, if you want to say less likely, and it's also time less likely to. You now calculate the reciprocal.
Have to convert it
when
to
you
R.
calculate the reciprocal, it gives you the impression, okay, if you want to quantify how many times it's less likely to, this one will be giving maybe 2 times, 3 times. But that 2 times, 3 times is more likely, less likely to. You cannot say 0 point so less likely to. Doesn't make sense. You understand? But most of the time, it's just to report it as less likely. And if we want to really know, that shows that if you are dealing with, if the exposure is dichotomous also, so you may change your coding. Like now, if you maybe you prison male and female, you care like this one. If it is this obesity now, that is less likely to. I can now recode it, and that's okay. Let's make the obese 0 and not obese 1. It will now give me how many times it will be greater than 1. How many? Because if he's telling me that the obese are less likely, that shows that the not obese are more likely. So when I now code it like that, I will be able to give me 2 point something. And so the not obese people are 2 point so time more likely to. But in a situation where the outcome, the exposure variable is maybe it's a continuous like age. So what you do, you just report it like that and say that you cannot go and record anything. You just report it like that and say that as the age increased by 1 unit, the likelihood of having cardiovascular disease decrease is less. But if let's say it's greater than 1, as the age increased by 1 unit, the likelihood of having cardiovascular doubles or 3 times move up. Don't worry, we'll see. Tomorrow is there, so tomorrow we'll try to mop up all this thing and do. At least we are through with the physics of it, so we'll be able to go into many data, more interpretation. I think we have learned something today.
All right, thank you, sir. Thank you, sir.
Yes. Of course, sir.
Biostatistics, honestly, it's been
yes.
Good night.
Okay, good night. Let me.
Tomorrow.
All right, good night, sir.
Good night, sir.